All right, so we're going to be wrapping up looking at molecular geometry, and we're going to be looking at chirality and summarize disymmetric and asymmetric molecules. So what is molecular geometry? Molecular geometry is 3D arrangement of the atoms that constitute a molecule. Molecular geometry is also known as molecular structure. It refers to the 3D arrangement of the atoms that constitute a molecule. So we have different molecular geometry. We have the linear geometry, we have the trigonal planar, we have the angular, we have the tetrahedral, octahedral, trigonal, and square planar. So for the linear molecule, we're actually talking about like a molecule that is actually arranged like in a linear fashion. So you can already find that this is carbon 4 oxide. Another example is nitric oxide. So carbon 4 oxide is arranged in a linear fashion. So it has a linear molecular geometry, and the bond angle is 180 degrees for linear geometry. And then we go to trigonal planar. Trigonal planar actually looks like a triangle. Yes, it looks like a triangle. An example of what we have in trigonal planar is the boron trifluoride. We also have the ethene molecule as a trigonal planar molecule, and the bond angle between them is 120 degrees. For angular molecular geometry is also known as V or bent-shaped geometry. It's also known as V or bent-shaped geometry. So for angular, it's actually in a bent format. An example is H2O, that's our water. Our example is H2O. You can already see that it's bent in a manner. And the bond angle we have between it is 105 degrees Celsius. Just some key things you need to know about the molecular geometry. Tetrahedral molecular geometry occurs when you have 4 atoms bonded to a central atom. When you have 4 atoms bonded to a central atom, the kind of geometry you have there is a tetrahedral geometry. For example, what we have here is methane. So this is carbon at the middle. Carbon is connected to 4 different hydrogen. This kind of geometry is tetrahedral. The bond angle is 109.47 degrees. And then we have octahedral. Octahedral occurs when you have 6 atoms bonded to a main atom. You have 6 atoms. In this case, what we're working with is silicon. So we're working with silicon hexafluoride. Silicon hexafluoride. So it has 6 atoms that are bonded to the silicon atom, and then what it forms is an octahedral. If you get to look at an octahedron, you will get to understand how all of these things relate and form that shape of octahedra. So it actually has a bond angle of 90 degrees. And then for trigonal pyramida, how it's in the form of a triangle, but it's in the form of a triangle. It has a triangular base, and the bond angle is usually greater than 90 degrees but less than 109.5 degrees. And an example of a compound that shows that is our ammonia. This is ammonia, NH3. NH3 has a trigonal pyramidal shape. And then the last molecular geometry we are looking at today is square planar. And square planar actually has like everything is on a square form on the plane you are referring to, and the bond angle there is 90 degrees. Now you have realized that of all of these things, we have the geometry that's actually planar geometry. What are planar geometry? Planar geometry is where you have all the bonds on the same plane. An example is linear. Linear is on the same plane. Trigonal planar on the same plane. Angular on the same plane. Square planar on the same plane. So you realize that this is a planar geometry, and this is planar geometry. So all of them are on the same plane. And something you need to note is that planar shapes or planar molecules cannot show chirality. Planar molecules cannot show chirality. They do not show chirality. So chiral planar molecules do not show chirality. They are usually achiral. So once you see a molecule that is planar, just know it's going to be achiral the moment you check for plane of symmetry. Yes, and it will definitely have plane of symmetry. This one has plane of symmetry. You can divide it like this. This one has plane of symmetry. You can divide like this. You can divide like this. Like any way you choose to go is actually going to like get you to have 2 sides. For this, it has a plane of symmetry and also has an external plane of symmetry. I've told you before, when you have double bond like this, you most likely have like an external plane of symmetry. Then for angular water, it has a plane of symmetry. It has a plane of symmetry. It has an axis of symmetry. Then for square planar, this is a plane of symmetry. This is xenon tetrafluoride. I've talked about it before. This is xenon tetrafluoride. So it has plane of symmetry, plane of symmetry, plane of symmetry, and an external plane of symmetry. That's like 4 different planes of symmetry for square planar xenon tetrafluoride. So, but then the only ones that are not planar here that are 3-dimensional shape are tetrahedra, octahedra, and trigonal pyramidal. If these things are well substituted, they will most likely have a chiral or produce a chiral molecule. For example, for tetrahedra, I've told you before, when you have 4 different substituents on the carbon, what you're going to have is a chiral carbon. And then if it is just one carbon having 4 different substituents, that molecule automatically will be chiral. Because when you do the mirror image, you cannot superimpose it on the particular image. An example is lactic acid, which we have used as an example prior to this time. So let's make progress. Something you need to note is that we have what is called dissymmetric and asymmetric molecule. Now, chiral molecules are always dissymmetric. What do we mean by chiral molecules being dissymmetric? It simply means that they always lack 2 important symmetrical elements, which are plane of symmetry, and point of symmetry. So chiral molecules will usually at least lack 2 important symmetry elements, that are plane of symmetry and point of symmetry, but they may not always be asymmetric. That means they may not always lack all the 3 elements. And the third one is the axis of symmetry. So what it means is that chiral molecules will usually lack at least 2, but they can also lack 3. So when they lack just 2, they are called dissymmetric molecules. When they lack 3, they are called asymmetric molecules. So asymmetric molecules are always chiral. An object can only exhibit chirality if it is either dissymmetric or asymmetric. It's either it's lacking the 2 of them entirely or it's lacking 3 of them. So that's something you need to take note of. And then finally, I would like to bring to your notice the fact that carbon is not the only molecule that can be able to exhibit chirality. You can have chirality in sulfur, you can have chirality in phosphorus, you can have chirality in nitrogen. And then these things, we are going to see them as we make progress in this particular course. So today, we have looked at different aspects of optical activity. We have looked at different aspects of symmetry operations and symmetry elements. We have looked at different aspects of chirality. And we have come to a conclusion of the chapter 1, which deals with optical activity and chirality. Try your hands on different exercises and see how far you can go. If you got any question, you could always ask. Thank you.